everyone, I'm Zhipeng. Today I'm going to talk about my thesis work, Pigasus, efficient handling of input-dependent streaming on FPGAs. So FPGA has demonstrated its success in accelerating many streaming applications from different domains. And the key benefit of FPGA is that it is a spatial architecture and allows hardware specialization. However, most of successful accelerations was focusing on the input-independent streaming application, where the operations on FPGA does not depend on the content of an input unit. For instance, in a streaming machine learning inference FPGA design, different images will be accessed by the same pipeline stages on FPGA yielding the same performance. Therefore, for this kind of input-independent streaming, the designs are usually static with fixed performance. However, such designs does not fit well for the input-dependent streaming, like intrusion detection and prevision system. And in this work, I'm going to we use the network intrusion detection and prevision system as a driving example to demonstrate how to efficiently handle input-dependent streaming behaviors on FPGA. So intrusion detection system is a critical network function to secure the network traffic. And it is widely deployed in many large enterprise and campus. And for instance, our FAMU campus also has its own intrusion detection systems. And as a real story, a few weeks ago, my own machine got infected by a malware, and FAMU intrusion detection quickly identified my IP and blocked my access to FAMU network. So this is a real problem, and it is critical to deploy such applications. So how does intrusion detection work? It checks the network packets, including the packet payload, against a large number of complex rules. And at the same time, it is also by nature input dependent. For instance, a packet that contains malicious payload, they will access more processing stages than the innocent counterparts. Because we need to check almost every single byte of network traffic against a large number of rules, this application is very compute intensive. And because of the input-dependent behaviors, this application is also very complicated. And due to the intensive computation requirements and the complexity of the designs, the state-of-art intrusion detection systems is struggling to keep up with the ever-increasing line rate. To give you a concrete example, we evaluate Snort 3, which is the state-of-the-art open source software intrusion detection system that equipped with the latest Intel HyperScan high-performance pattern matching library. So this graph, I'm showing you the number of cores needed to reach 100 gigabit per second. On the x-axis, I'm showing you the different empirical traces we evaluate. And on the y-axis, I'm showing you the number of cores. Note that this number is extrapolated from the single core performance number, and we assume ideal scaling. And even under the ideal assumption, we still need 4 to 21 servers with 1 to 6 kilowatts if we use this software approach. And this is obviously not power and cost-efficient option. So in this work, we propose Pigasus, which is a 100 gigabit per second intrusion prevision system implemented on a single server. Pigasus composed of a FPGA-based SmartNIC, which processes the network packets in line, and a multi-core CPU, which handles the corner cases for FPGA. Now let's compare the performance with between Pigasus and the software baseline. So in this graph, you can see that among all the empirical traces, Pigasus consistently use a handful of cores. Overall, we only need like one server with less than 200 watts in order to achieve 100 gigabit per second. And this is order of magnitude efficiency improvement over the software baseline. So what's the secret sauce behind Pigasus? Let me start with the missing opportunities of prior work. There have been a lot of work using FPGAs to accelerate intrusion detection system, but most of them are looking at particular tasks. And these tasks are usually implemented in a fixed performance way, where they over-provision for the worst case traffic. Therefore, it could be very resource consuming. And our first insight is that we should tune for common case. We need to allocate more resource to improve the common case traffic performance while handling the uncommon case in a resource efficient way. And this makes it possible to extract the maximum performance using minimum resource. A natural objection to this approach is that a highly common case tailor design may cause overfitting for the particular deployment scenarios. And once the deployment scenario changes, the same design may either cause performance degradation or resource waste. And to tackle this problem, we propose a disaggregated architecture and a dynamic adaptation mechanism such that users can easily retune the design at both compile time and runtime to retain the efficiency. So I have briefly introduced this work. Now I'm going to dive into the details. And in the first part of this talk, I will focus on the first insight, which is tune for common case. And in the second part of our talk, I will talk about our second insight, a disaggregated architecture and a dynamic adaptation, which addresses the brittleness caused by the common case tailoring design. And finally, I will show you the end-to-end evaluation result. So before I talk about our idea, let me give you a little bit more context of how IDS and IPS work. So the packet comes into the system, and first of all, it will be parsed to extract the metadata information, such as the IP address, the port number, and the packet size. And then the TCP packets need to be reconstructed in order to keep the byte stream flow. So for instance, some of the TCP packets may arrive out of order, and here the flow reassembly logic will reorder them for the pattern matching check. And the pattern matching check is divided into two parts. The first part is called multi-stream pattern matching, which is the most compute-intensive modules in a intrusion detection system. So here, the multi-stream pattern matching module extracts one of the highly selective stream patterns from each rule. So basically, tens of rules, each of them contributes one of the stream patterns, and these stream patterns will be grouped together to form a structure such that every single packet will be checked against of tens of thousand rules in parallel. And this pattern is also called fast pattern. And if a packet does not match any of the fast pattern, then it is safe to say that this packet is an innocent packet, and we can forward out this packet. On the other hand, if a packet match any of the fast pattern, this packet will be considered as a suspicious packet, which requires further evaluation. And in the full matching, we will fully evaluate the rules, including other fields, for example, other stream patterns or regular expressions. And the goal of this work is to support 100 gigabit per second with tens of thousands rules and 100K concurrent flows using only a single server. And the key is that we need to efficiently handle the input-dependent behaviors. For instance, you may already notice that the suspicious packets require more processing stages than the innocent packets. And similarly, for in-order packets and auto-order packets, the operations could also be different. So as I said earlier, there have been a lot of attempts to use FPGA for accelerating the intrusion detection system, and most of them are focusing on each of the pieces in the end-to-end system, and use a worst-case oriented design. To scale existing algorithm to 100 gigabit per second, we will use a lot of on-chip memory resource. And even though the FPGA we are using in this project is a pretty high-end FPGA, the Intel Stratix 10 MX FPGA, the on-chip VRAM resource is insufficient. It's only about 16 megabytes. We cannot fetch all of the tasks on a single FPGA. Now you may wonder, why don't we just offload a single task on an FPGA? Actually, this is most prior work we're doing. However, by profiling the SNOT software baseline and apply a simple Amdahl's law analysis, we can come up with a solution that the single task offload is fundamentally insufficient in addressing end-to-end performance. So in this graph, I'm showing you the performance breakdown by profiling SNOT, our software baseline. On the x-axis, it is still the different traces. The y-axis shows you the fraction of CPU time spent on each of the tasks. As you can see that there is no single dominating task. And even if we assume we can achieve ideal acceleration, for instance, the multi-stream pattern matching can be accelerated by FPGA using 0 time and without any FPGA CPU communication overhead. The best we can achieve end-to-end is 2x speed up, which is far away from 100x we are targeted at. And to address the problem, our insight is tune for common case. In particular, we need to identify and accelerate the common case traffic, and that's a key to achieve high end-to-end performance. And secondly, we need to handle the uncommon case in a resource-efficient way, which is a key to reduce the resource cost. So the idea itself sounds straightforward, but the hard part is that we need to apply this idea to the different places and different levels of the end-to-end system. At the end-to-end system level, we propose FPGA-first architecture. And for the flow reassembly module, we propose a fast flow path reassembly design. For the multi-stream pattern matching module, we propose a hierarchical pattern matching. And by combining these three ideas together, which share the same theme of common case tailoring, we can achieve both high performance with low results. And in the next couple of slides, I'm going to dive into the details of these three ideas. Let me begin with FPGA-first architecture. So we argue that to achieve high performance for this input-dependent application, we need to flip the traditional role of FPGA and CPU. And in an FPGA-first architecture, FPGA becomes the main processing unit, and CPU becomes an offloader, which handles the complex and rarely triggered cases for FPGA. And in this way, the common case traffic can be entirely processed by the highly parallel data path on FPGA to enjoy high throughput and low latency. In fact, we have observed that among the empirical traces we evaluate, about 95% of the packets will be entirely processed by FPGA, and only about 5% of the packets would ever trigger CPU processing. And in this way, we will save the limited and valuable FPGA resource such that this real trace can be handled on CPU without using FPGA resource. However, this idea is very challenging to realize because at this point, we still need to implement the reassembly module and the multi-stream pattern matching module on FPGA. And as I said earlier, if we simply using existing algorithms, that won't fit on single FPGA. So now let's move to Pigasus reassembly. The key takeaway here is that we use a fast flow path design where we separate the in-order packets and out-order packets processing. And the flow path is responsible for handling the out-order packets. And at that path, we can apply a memory-dense data structure, which may have some non-deterministic performance, but that will save the memory resource we need. So overall, our reassembly logic only consumes 3.4 megabytes of DRAM, saving about more than 60 megabytes of memory compared with existing work. So prior reassembly work was allocating fixed size memory for each of the out-order flows in order to achieve constant performance. And in this approach, the memory consumption scales with a number of out-order flows. For instance, that work allocates 64 kilobytes static space for each of a flow. This will cause two problems. The first problem is that it wastes a lot of memory because most of the out-order flows does not need 64 kilobytes of memory. And another problem is that for some of the flows, which actually require more than 64 kilobytes of memory, these flows will not be supported by prior work. These flows will be considered as exceptional flows. And if like 1% of 100K flows are out of order, which is a typical number, then we will need 64 megabytes of on-chip memory to store these packets. And Pigasus use a different approach. In our approach, the memory scales with a number of out-order packets instead of flows. In order to achieve that, we store the packets in the order they arrive. So basically, the packets from different flows, they share the same big unified packet buffer. And this brings us two benefits. The first benefit is better memory utilization, because on average, one out-order flows only have 3 out-order packets. We can save a lot of memory space. And it also reduces the chance of exceptional flows. If a flow has long out-order packets, with the single big unified packet buffer, we can support such flows. And overall, we only need 5 megabytes of memory space to store these packets. And to further reduce the consumption of block RAM, here we map the unified packet buffer to another type of memory technology called embedded SRAM, which is slower than the on-chip DRAM, but still fast enough to support continuously 100 gigabit per second read and write. Since we store the packets in the order they arrive, how can we sort the packets in their flow order? To achieve that, we developed 2 separate structures. So one is called flow table, where we keep track of a sequence number of each of the flows. And another structure is a linked list, where we within a flow we track their we track the packet orders. And because the linked list would cause non-deterministic performance, for instance, if it happens to trigger the linked list traversal, it will take us many cycles to get executed. And to isolate the performance impact of this non-deterministic execution, we develop a faster flow path, where the faster path is responsible to handle in-order packets, which is 95% of the overall packets. And the flow path will handle this auto-order packets, which execute the auto-order packets in the background. And because we have two separate paths, the non-deterministic performance will be isolated, and we can use a more memory compact structure to track the auto-order flows. Now let's move to Pigasus multi-stream pattern matching. So the key takeaway of Pigasus of our approach is that we have a hierarchical filters where we allocate enough replicas of compact front-end filter to catch up with 100 gigabit per second line rate in the front. And the back-end filter only need to catch up with the hit rate of the previous level filters, such that we can save we can use less number of replicas for backend filter to save the memory. So overall, we only need 3.3 megabytes of VRAM, saving about 22 megabytes of VRAM compared with prior algorithm. So now let's take a look at the design options we have. Most of our work was based on state machines. Basically, we take the stream patterns and generate a non-deterministic automata or deterministic finite automata to do the pattern matching. And if we just apply the tens of thousands fast patterns, it would take 23 megabytes of VRAM. Another approach would be map the high performance hyperscan literal matching engine from software to FPGA, which is a hash table based solution. We have profiled that a simple, straightforward porting would take 25 megabytes of VRAM, which can support both header, both faster pattern matching and the header matching. And in Pigasus, since we applied a hierarchical pattern matching design, we only need 3.3 megabytes of VRAM. And our approach is also hash table based solution. And since our design is so memory efficient, we can actually use the FPGA on chip memory to complete more work. For instance, we extract the non-fast stream pattern matching from the full match stage to this multi-stream pattern matching stage. And our idea is that we need to utilize the performance in the memory trade-off in order to save the memory. And on FPGA, to achieve high performance, many times you need to utilize the data parallelism. Basically, you need to process more data in parallel. And this, to do that, you need to replicate your structures by multiple times. And this will cause more memory consumption and logic consumption. Our key observation is that there is no need to keep up with 100 gigabit per second everywhere. And for the places where we don't need such high performance, we can trade off the performance by saving the memory resource. And following that idea, we develop our hierarchical filters. The front-end filter, we allocate enough replications of that in order to catch up with 100 gigabit per second. But for the later stages, we only need to catch up with the hit rate of a previous level. And eventually, when the data reaches CPU, only about 5 gigabit per second traffic. And for each of the suspicious packets, we only need to check 2 rules. So in this design, the front-end filter is handling the common case, which is 100 gigabit per second data and tens of thousands rules. And the later stages only need to handle the uncommon case, which are the suspicious packets and a handful of rules. Now let's put it all together. So the worst case-oriented FPGA designs are too expensive to be practical on FPGA. And at the same time, the single task offload is insufficient to achieve end-to-end speed up. And our insight is that we should tune for common case, which allows us to achieve high performance with low resource consumption. In particular, we propose 3 ideas: FPGA first architecture, faster slow path reassembly, and hierarchical features. By combining these 3 ideas together, we can support 100K flows, 10K rules running at 100 gigabit per second, only using half of FPGA resource. So far, like tuning for common case seems very efficient to achieve high performance and low resource cost. But that only applies to the specific traces. So what if the input changes? So here I'm going to show you the diverse behaviors between the traces. In this figure, I'm showing you the percentage of packets that passes each filter and enters the next filter. And again, on the x-axis, I'm showing you the different traces, and on the y-axis, I'm showing you the percentage of the packets. So let's first zoom into the last 2 traces, where we can see that the intersection of faster pattern filter and the header filter is already very effective. The non-faster pattern filter doesn't really filter out too much traffic as the header matching as previous to orthogonal filters is already effective enough. And for this particular traces, users can actually just remove a non-faster pattern matcher from the design to save a resource. However, such designs may not work for the rest of the traces, where you can see that the non-faster pattern matcher is indeed effective. So the point we want to make is that a common case specialization may not suit for our deployment. It could either result in performance degradation or resource waste. So since we are using FPGA, we can reprogram the designs in order to fit different scenarios. But for a long time, FPGA development have been following a static mindset, where FPGA is treated as an ASIC. Once the design is deployed, it never changes. But we argue here is that for input-dependent applications, we should make the best use of FPGA programmability in order to adapt to different scenarios while retaining the high efficiency through specialization. So I had talked about our first insight, the common case tuning, and the problem caused by common case tuning. Now, I'm going to move to the second insight, the disaggregation and the dynamic adaptation, which addresses the brittleness caused by the common case tailoring design. In particular, I will talk about 2 ideas: the disaggregated architecture, which allows users to easily retargeting the design at compile time, and then the dynamic spillover mechanism, which can aggregate the birthday traffic at runtime. So, the problem of our common case tailoring design is that it is so brittle. If the deployment changes, the same design may not become efficient. Actually, in our initial development of Pigasus, the Pigasus 1.0, we following the traditional design mindset of FPGA, where the outcome is that we have a single design that's specialized for 100 gigabit per second for our empirical traces and for the Stratix 10 MX FPGA. And the hope is that this single design can fit different scenarios, which is obviously not the case. For instance, for one of the deployment, the faster pattern matching could be the bottleneck. For another deployment, the non-faster pattern matching module could be the bottleneck, right? Sometimes users may even have different performance targets, let's say like 50 gigabit per second. So the same device may not be efficient for all of the deployment environment. And to address the problem, we propose Pigasus 2.0. And here, instead of generating a single design, we provide a space of designs, and we let the users to pick a most suitable configurations at compile time. And each of the design itself is still highly specialized for the particular deployment environment in order to retain the efficiency. And to realize Pigasus 2.0, we need disaggregation and parameterization. So we need to disaggregate the tightly coupled, highly specialized 100 gigabit per second pipeline into individual streaming services to allow more efficient scaling. And we also parameterize each of these streaming services to provide different performance, capacity, and resource trade-offs for users to pick. And here I'm going to show you a simple example to give you an idea of the benefits of disaggregation and parameterization. And here we make a case that the second level filter becomes a performance bottleneck. And with existing Pigasus 1.0, users either have to dig into the code base and do a manually change, which could be very time consuming and error prone, or replicate the entire pipeline in order to catch up with performance target. And with Pigasus 2.0, everything becomes easy. Users can easily scale up or scale out the performance bottleneck. And compare with this pipeline replication, we only introduce a little bit over. Compare with the pipeline replication, we will save a lot of resource. And since we need users to pick up the configurations, it is important to provide very high portability and design productivity such that users can easily explore different design choices or hardware targets. However, the traditional wire abstraction for streaming application limits the desirable portability and design productivity. And by wire abstraction, I'm referring to the case where the streaming modules are explicitly connected together through wire or FIFOs at RTL level. And if you want to change the way it connects, or for instance, scale up particular modules, users have to hand-coded or hand-modify the RTL code, which could be time-consuming and also error-prone. And our solution is that we should have a communication abstraction where all of the streaming services, they are logically connected to a common communication abstraction. They are not directly connected. Logically, they are not directly connected together anymore. They are connected to the single box. And to get the efficiency out of this abstraction, at compile time, here we reuse a service-oriented framework. And this framework allows us to automatically generate the RTL implementation from Python level. And with the help of this framework, users can do the change at the Python level to easily explore different design choices and quickly recompose them together and generate the efficient hardware implementation. And at this abstraction, we also provide a rich set of features, such as scaling out and instrument to improve the debuggability. So with disaggregation, parameterization, and common case abstraction, users can easily retarget the device at compile time. But what if the traffic changes at runtime? Here I'm showing you a simple example where most of the time, a single filter 2 is sufficient to handle the traffic. However, now we have a burst of packets that will stress this filter 2, which will cause the pipeline stalling and eventually packet drop. As I said earlier, a worst case over provision could be too expensive to be practical. And big buffers is also impractical in this case, because at 100 gigabit per second, any small slack in the traffic will easily overflow the megabytes of packet buffer in our system. And even if we have an infinitely big buffer and super fast, it is still not because of the latency concerns. It is still a good solution. And our solution is that we should temporarily introduce more compute power to absorb this spillover traffic. This idea itself is generic and can be there could be many design options. It could be applied to any common case services, and it could be implemented in different ways, as long as this backup compute power, the backup instance can be brought up on demand. For instance, if a filter 2 becomes a bottleneck, we can route the spillover traffic to CPU, and we can temporarily brought up a partial reconfiguration instance on FPGA. We can even route the traffic to another FPGA, which can be dynamically brought up and load. So I have talked about the second insight, disaggregation and dynamic adaptation, which addresses the brittle needs of common case tailoring. Now let's move to the evaluation. So I will start with a comparison with the software baseline. And I have shown you the same graph in the beginning of this talk. And here you can see that Pigasus use 2 order of magnitude cores than the software baseline. And the core saving also gave us power saving and cost saving. So here I'm showing you the power consumption of software baseline and Pigasus. And as you can see, Pigasus also use 2 order of magnitude less power. We estimate the total cost of ownership, which includes the energy consumption over 3 years and the capital cost of buying the hardware itself. The Pigasus TCO is less than 1/3 of Snort solution. So Pigasus is better than software baseline, but how is it the best we can achieve? So to answer that question, we compare Pigasus with 2 data points. The first data point is that the single task acceleration, where we assume that the multi-stream pattern matching module can be accelerated ideally, where it is 0 cost and 0 communication overhead, which is the blue bar in this graph. And as you can see, by just accelerating a single task, we still need hundreds of cores to reach 100 gigabit per second. The second data point is ideal acceleration except regular expression. And in this case, we assume that only the regular expression is executed on CPU, and the rest of the tasks are free. And note that the regular expression is only part of the original full matching task. And this is basically the best we can achieve with the current Pigasus architecture. And as you can see, the Pigasus performance is very close to this ideal acceleration. So I have talked about the from the previous evaluation, basically demonstrate the effectiveness of common case tuning. Now let's move to the evaluation of disaggregation and dynamic adaptation. So by disaggregating the highly customized pipeline, we would introduce a little bit resource overhead if they are under the same setting. But the real benefit of the disaggregation is that if the deployment environment changes, the disaggregation will allow more efficient scaling. For instance, I have shown you this example before, the pipeline replication versus bottleneck scaling. And this graph shows the resource consumption of these two solutions, normalized to the single 100 gigabit per second pipeline. On the x-axis, I'm showing you the different types of resources. And as you can see, the pipeline replication requires 2x more resource, 2x resource compared with 100 gigabit per second pipeline. And for the bottleneck scaling, we only use about 10% of a more resource compared with 100 gigabit per second pipeline. So overall, by comparing the pipeline replication and bottleneck scaling, we can see that the bottleneck scaling will save a lot of resource. The second example is that what if the performance target is different? Here I'm showing you that if users want to map to use Pigasus for a 50 gigabit per second environment, and today the user have to use the Pigasus 1.0, the 100 gigabit per second pipeline. But with Pigasus 2.0, users can tweak the design such that we can remove the unnecessary components. And in this graph, I'm showing you the per module VRAM consumption when mapped to 50 gigabit per second. And on the x-axis, I'm showing you the different modules in the design. And on the y-axis, I'm showing you the normalized resource consumption to a 100 gigabit per second pipeline. And as you can see that some of the modules are not performance dependent. For instance, the reassembly module, which is expected because the resource depends on the flow table capacity size. But for some of the modules, like the filters, the faster pattern filter and the non-faster pattern filter, since we are targeting at 50 gigabit per second, we can shrink the filter down to the half of the size. And overall, we only need to compare with a 100 gigabit per second pipeline, we will save about 30% of the resource. Is there a question here? Oh, okay. Now let's take a look at the effectiveness of a communication abstraction. So we argue that with this common communication abstraction, it's easy to map the same design to different platforms. And here we are targeting at a multi-FPGA platform because we think the multi-FPGA is going to be the trend as the network LAN rate keeps increasing and the capacity requirement keeps increasing. And with a common communication abstraction, users don't have to change any RTL code, and all of the processing services, they stay the same. So users only need to tweak the recomposition at Python level in order to map a Pigasus design from monolithic FPGA to this multi-FPGA setting. And the second example is that if users want to explore different choices, for instance, if a user wants to cut the pipeline from different cutting points of a pipeline, for instance, the bottom design is we cut the pipeline between the header services and the non-fast pattern services. And to achieve that, we only need to change 17 lines of a Python code without changing any RTL. Finally, let's take a look at the effectiveness of dynamic spillover mechanism. And here we apply this idea to the non-fast pattern matcher, and we create a spillover path to CPU such that when the birthday traffic comes, that cannot handled by the default non-fast pattern matcher, CPU will use more cores to process this packets. And in this graph, I'm showing you the zero loss throughput improvement over the design that without the spillover mechanism. As you can see that for some of the traces, like mixed 2, mixed 5, normal 1, normal 2, the performance stays the same, which suggests that the default non-fast pattern matcher is sufficient to handle such cases. But for the birthday traces, like mixed 1, mixed 3, and mixed 4, we observed about 40 to more than 200% more zero loss throughput improvement, where the CPUs can handle this birthday traffic on demand. Now let me conclude. The traditional static and fixed performance FPGA designs is inefficient when handling the input-dependent streaming applications such as intrusion detection and prevision system. And our first insight is to tune for common case, which allows us to extract the maximum performance using minimum resource. And our second insight is disaggregation and dynamic adaptation, where we can address the brittleness of a common case tailoring design by letting users to retune the design at both compile time and runtime to retain the best efficiency. So Pigasus 1.0 is already open sourced, and we are planning to release in Pigasus 2.0 very soon. With that, I'm happy to take any questions.